Okay, so we were discussing the frequency domain analysis and the theorems in frequency domain we were discussing. We discussed some theorem like mesh analysis, nodal analysis, and we discussed other theorems also. Today's lecture will focus on source transformation first, and then we move to Thevenin's and Norton's theorem. So we have already covered the source transformation for the DC circuits. So here in frequency domain, we are just taking up the numerical to understand the theorems because the lecture has already been covered. The theory behind is already covered. So in the source transformation, we have a problem like this. Calculate Vx using source transformation. So Vx is basically the potential across the 10 ohm resistor. We have to determine this Vx using source transformation. You can solve this problem by any other method, whether it is Thevenin's, Norton superposition or any other method. But however, here we will solve the problem by source transformation. If you remember, we discussed that whenever you are solving any problem in frequency domain, the frequency remains constant. So omega remains constant. Moreover, all the values of the RLC has to be converted in ohms. So usually we are dealing with the impedance. So if you have some inductor or a capacitor in a network, then you convert that inductance and capacitance into impedance using the concept of inductive reactance and capacitive reactance XL and XC. So all the unit of the parameters has to be in ohms, then only we can move forward. Now coming back to the source, if we observe the source, so source is given in the polar coordinate. Here we have some magnitude that is 20 and the angle that is minus 90 degree and the unit is in volt. So we can see that positive negative symbol has been given. So it means that this is a voltage source and the voltage source magnitude is 20 angle minus 90. We have to determine the potential Vx using source transformation. You know that in source transformation, we convert the voltage source into current source with the adjustment of the resistor value. Okay, so the current is basically potential divided by the resistance, or voltage is equal to current multiplied with resistance. So here the resistance remain the same. One is in series and another is in parallel. So when voltage source is there, it will be in series. When current source is there, it will be in parallel. However, the potential drop, or the rather the impedance, if we say, rather the impedance or the terminal characteristic of voltage by current will remain the same. So that is the concept behind the source transformation. So let us solve this problem in source transformation. We have one source, voltage source, and one resistance that is 5 ohms. These two are in parallel. So we have a voltage source and a resistance in parallel and the remaining part of the network. So if I take this part of the network and convert it into a current source in parallel with a resistance, this is possible because it will not disturb the other part of the network. Other part of the network will be as it is. It will not be disturbed. So the current source magnitude, in accordance with the Ohm's law, we have the potential divided by the resistance. So voltage is equal to 20 angle 90 minus 90 we have, and then the resistance value we have the 5 ohms. So we get a current of minus J4. Okay, you know that J is basically iota, which is angle 90 degree. So here we have the 4 ohm resistance which is in parallel with a current source of Is whose value is minus J4. Now one thing we have to understand in source transformation is that the polarity of the voltage source, the positive polarity direction will be the direction of the current source. So this is the voltage source and this is the current source. So here we will see the positive polarity of the voltage. In that direction we will be giving the current source direction. If we have the positive polarity downward and negative upward, then we have the current in this direction. However, we'll go by this voltage polarity. Now our circuit from this end to this end, it has been modified. We have got a modified circuit where we have a current source instead of a voltage source, and we have a resistance in parallel. Now let us operate on this part of the network. If I operate on this part of the network, this is the equivalent impedance. We can obtain the equivalent impedance of these two part, that is Z1. You know that when two impedances are in parallel, then we can write the Z equivalent is equal to Z1 into Z2 divided by Z1 plus Z2. So here we can take the value of Z1 is equal to the 4 ohm resistance, and the Z2 is equal to the 4 plus 3. Okay, now understand, here we have a resistance and inductance, then the impedance will be equal to R plus J time XL. Okay, the impedance will be R plus J time XL. Now we can make use of these two impedances. One we take, this one is Z1 and another one is Z2. Z2 is the combination of the resistance and the reactance. Then we can write this Z equivalent formula to find the equivalent impedance of this, which comes to be 2.5 plus J times 1.25. Now my circuit is, I'm having one impedance. This is Z equivalent, which is coming as the Z1 parallel with Z2. Now, if I want to convert these current source into voltage source, then I will be using the concept of current to voltage conversion. So I will convert the current source into voltage source. Now the arrow symbol is given upward, so we have positive and negative here, and the voltage we are having as the product of the current Is, which is this one, and the Z equivalent that we have got from these two quantities, which is equal to I am writing Z1 here because I have written Z1 here. So 2.5 ohms minus J times 1.25 ohms. So my net voltage source is coming to be 5 minus J10, which I can put it here, the voltage source. Now you see the circuit, all quantities have come in series. We have got the resistance, inductance, another resistance, capacitance and resistance, all are in series. We have to determine Vx, which is the potential across the 10 ohm resistor. It means we will not disturb this part of the circuit. We can have the total addition of this one, but we will not disturb this part of the circuit because there I need to calculate the value of Vx. So how I can calculate the Vx? I can calculate the value of Vx using voltage division rule. Now my circuit has been reduced into a much smaller format. Now what does the voltage division rule says? Voltage division rule says that the Vx is equal to the source voltage Vs multiplied with these impedance. If I take this one as Zn, so Zn divided by Zn plus, if I take this one as Z equivalent, so I will be having Zn plus Z equivalent. In this way I will get the value of Vx using the voltage division rule. So the final answer of the voltage is this one. If the same problem, if we solve by some other method, whether it is Thevenin, Norton or superposition or KVL or KCL, if I solve this problem by mesh analysis, I should have taken two currents, I1 and I2 here, and then I should have written the KVL equation in this loop, KVL equation in this loop, and then I need to determine the current I2, and then I can determine the potential Vx. But source transformation is much easier when you can reduce the circuit from one form to the another. Now we'll go for the Thevenin's theorem. Okay, so in Thevenin's theorem, we know that any complex circuit can be reduced into a voltage source, that is the voltage Thevenin, and in a series with one impedance. Now I will say that is Z Thevenin. Earlier I said that R Thevenin in the DC part. Now the same concept will be converted to the impedance, that is Z Thevenin, and we will have voltage Thevenin here. Okay, so any complex circuit can be reduced into a voltage circuit, voltage source, that is voltage Thevenin, in series with a impedance, that is Z Thevenin. Let us see how to solve this type of problem. So the problem is obtain the Thevenin's equivalent at the terminal AB. So we have a terminal A here and terminal B here. We have to obtain the Thevenin's. Now you know that Thevenin's voltage is basically the open circuit voltage at terminal AB. So where you need to determine the Thevenin's voltage, you open that part of the network and you obtain the voltage across the two terminals. This way of solving can be done by any other method like mesh or nodal or superposition. That is up to the user who is solving this problem. And the resistance Thevenin, R Thevenin, you have to obtain by short circuiting the independent voltage source and open circuiting the independent current source. Dependent current source or dependent voltage source we will not touch. We will not touch that. Only the independent voltage source and independent current source we have to short circuit and open circuit. So let us see how to solve this. First, we will check whether all the impedances are in ohms or not. So I see that all the parameters are in ohms. So I need not to convert the Henry to ohms or Farad to ohms. It is already in ohms, that is in impedance. Source is basically 120 angle 75. That is basically a voltage source. So what is the open circuit voltage at terminal AB? Now I can consider these impedances as Z1, Z2, Z3 and Z4. All the parameters you can convert them into impedance with Z1, Z2, Z3 and Z4, and then you can reduce the circuit. So from this circuit, if I obtain first the Z Thevenin, what I need to do? I need to short circuit this voltage source and then I have to reduce the circuit in a much better format. So here I have the terminal A and here I have the terminal B. Now I can redraw this circuit into better format so that I can apply the other theorems. So the circuit has been reduced in this format. Now I want to determine what is Z Thevenin here. That is, what is the equivalent impedance seen in the terminal. So let us do that. What I will do is that first I will calculate the parallel operation of these two quantities and I will write this one as Z1. I will do the parallel operation of these two quantities or the parameter and then I will write Z2. Now Z1 and Z2, if you see, after that it will come in series because I need to operate in this zone. So let us obtain Z1 first. Z1 is the parallel operation of 8 and minus J6, which I am getting 2.88 minus J 3.84. This is in accordance with Z1, Z2 by Z1 plus Z2 when two impedances are in parallel. Similarly, 4 ohms and J 12 ohms are in parallel, which will give me 3.6 plus J 1.2 ohms. Then the Z Thevenin will be the sum of Z1 plus Z2 because that two impedances are in series. So this is the Z Thevenin that I am getting. Now I will calculate the voltage Thevenin. Voltage Thevenin is the open circuit voltage at the terminal A and B. So this circuit I have modified into a better format so that I can apply the theorems to obtain the voltage Thevenin. Now how do I obtain the voltage Thevenin here? If I am applying a KVL equation in this particular loop, then I can apply what is the voltage Thevenin. Means the voltage potential of A minus voltage potential of B will give me the open circuit voltage here, V Thevenin. For that, I need to determine what is the voltage drop across this capacitor, what is the voltage drop across this 4 ohm resistor. Now, if I obtain the current I1, what is the current I1 flowing here, what is the current I2 flowing here, then I can determine what is the potential drop across the capacitor and the resistor. I can obtain the current I1, using the concept of the current division rule I can obtain, or I can obtain this in any other method. Okay, so what I can see that these two 8 ohms and J6 ohms, these two are in series, then this will become one impedance, and J12 ohms and 4 ohms are in series, so this will become another Z2, so Z1 and Z2. So I can obtain the value of I1 and I2 using the concept like I'm having a voltage source here, I am having one impedance here which is Z1 and another impedance which is Z2. So the current I1 which is flowing here is basically the potential V, because these three are in parallel. So the same potential will be there across Z1 and Z2. So I can determine the current I1 or I2 using voltage divided by Z1 or Z2. Okay, so I am getting the value of I1, I am getting the value of I2. Once I am getting the value of I1 and I2, I can apply the KVL either in this loop or in this loop, any other, either in this loop or in this loop. Then I can determine what is the voltage Thevenin. If I am applying a voltage Thevenin equation in the KVL equation this, I can determine what is the voltage Thevenin, that is the open circuit voltage at the terminal AB, by applying the KVL equation either at the top loop or at the bottom loop, anywhere. So I'll get the voltage. So voltage Thevenin also I have got, Z Thevenin also I have got. Now my circuit is, we have a voltage Thevenin in series with the Z Thevenin. So this is Thevenin's theorem. Now, if we have one dependent source, then how to solve that problem? Find the Thevenin's equivalent of this particular circuit. So here you observe that we have a dependent current source because we have an arrow. So it is a dependent current source. So can we solve this problem using the same method which we adopted in problem 1? No, it is not possible. Why? Because we have a dependent current source. So we can't obtain the Z Thevenin directly using the concept of series and parallel. We have to apply some other method. So let us see that how to obtain that. Now, first we will determine what is the voltage Thevenin. So in order to determine the voltage Thevenin, you can apply any concept with whatever we have studied, whether it is KVL, KCL, superposition or any other theorems. Whatever theorem is good to you, that theorem you can apply in this circuit to obtain the voltage Thevenin at the terminal AB. So the open circuit voltage at the terminal AB is basically the Thevenin's voltage. Now here if we apply the KCL and the KVL rule, combination of KCL and KVL, then I can obtain what is the voltage Thevenin. So at this particular loop, at this particular junction, I can apply the KCL and then I can apply the KVL in this particular loop. Then I can obtain what is the voltage Thevenin, that is the open circuit voltage. These all concepts we have discussed very detailed in the DC circuit, and here in AC circuit, only difference is that instead of a resistance, you have to operate with impedance. Now, once we have got the value of voltage Thevenin, now the time is to determine the Z Thevenin. So, due to the presence of this dependent source, I can't obtain the Z Thevenin using series parallel concept. Rather, what I will be doing is that I will connect a current source of some amplitude, and then I will determine the Z Thevenin as the voltage divided by the current. So here I have connected one current source. This current source, I can connect any current source of any magnitude depending upon the wish, or I can connect a voltage source also, some voltage source of 1 angle 0 or a current source of 1 angle 0, anything I can connect. So here we have connected 3 angle 0 in this particular problem taken from one of the book. So there they have taken 3 angle 0 and then they determine what is the potential Vs across the terminal of the current source. Then the Z Thevenin is equal to voltage source by current source. Only thing is that the current source 15 angle 0 you have to open circuit. So you have to open circuit this 15 angle 0, because to obtain the Z Thevenin you have to deactivate the independent sources. So here we have independent current source which you have to deactivate using the open circuit, and then you have to connect a source, known source, and determine the potential Vs, and then you can determine the Z Thevenin by Vs by Is. The intermediate step you can solve by any other method, whether it is a KVL or KCL. So we have got the Z Thevenin and voltage Thevenin. So remember, whenever you have any dependent source in the circuit, then in that particular problem, please solve either connecting a voltage source or connecting a current source to determine the Z Thevenin. The same we have done for the DC circuit also. We'll go for the Norton's theorem. In Norton's theorem, you know that the Norton current is basically the short circuit current at the terminal AB, whatever terminal you need to determine, and Norton resistance R Norton is equal to the Thevenin resistance, which is can be obtained using open circuit voltage by short circuit current. Open circuit voltage you can write the Thevenin's voltage, and short circuit current you can write the Norton current. So you can use this concept to determine the Norton current and the Norton resistance. So here the problem is to determine the current I naught. So current I naught is flowing here in this part of the network using Norton's theorem. It means this is my terminal A and this is my terminal B. If these terminals are not marked also, you have to take that as the terminal, because you have to determine the I naught. So where you need to determine the variable, that will be the load resistance, or I can say the load impedance. So these two resistance and inductance in parallel will become the ZL value. Okay, you have to sort this to obtain the value of I Norton. You have to open circuit this to obtain the R Thevenin. Okay, or rather I can say Z Norton and Z Thevenin. Now, first we will try to obtain the Z Norton. So Z Norton is equal to Z Thevenin, which is obtained by open circuiting the terminal. So whatever the parameters are connected, that you open circuit. So we have open circuit here. Now the independent sources, we have a voltage source and a current source. So voltage source will be short circuit and current source will be open circuit. Note here, this should be done only for independent sources, not for the dependent source. We have only independent sources here. So we have short circuit this part and open circuit here. Okay. So now my new network, I have obtained it. I can determine the value of Z Norton. Since this is sorted, I can sort this part also. Okay, I can sort this part also. Now, if I see the Z Norton, I can see that this is at potential 0 volt. Okay, because I'm having this one as grounded. So whatever the impedance is seen here at this terminal, that will be the Z Norton, which is coming to be 5 ohms. So Z Norton is equal to 5 ohms. Now coming to solve the value of I Norton. So I Norton is basically the short circuit at the terminal AB. Whatever the terminal across which the load impedance is connected, there you will be short circuiting, and you can apply any other method, whether mesh or nodal. Here I am applying the mesh analysis. Okay, so I have written the mesh analysis for 3 independent loops. Now see, you have a current source here between two meshes, I2 and I3. If you have the current source between I2 and I3, you will be having a super mesh concept that we have studied in the previous lecture where we discussed the super mesh. So I2 and I3 combination will become a super mesh because you have a current source in between the two meshes. So even we are solving this problem using Norton's theorem, but we require the concept of mesh analysis also, super mesh analysis also, which takes the concept of KVL and KCL. So I have written 3 equations, 1, 2 and 3. First 2 equations are coming from the KVL, Kirchhoff's voltage law, and the third equation is coming from KCL at the super mesh. So we can see that I3 current is flowing upward, I2 current is flowing downward, and your net current is flowing upward. So you can write this equation of KCL at the super mesh, and 2 equation, one super mesh equation and one other mesh equation, to form the 3 equations in 3 variables. So I have the variable I1, I2 and I3, which I can obtain by solving these 3 equations. Once I solve the value of the 3 equations, I'll getting the solution of I1, I2 and I3, and I need to determine the value of I naught. This is my question was given, what is the value of I naught? So I have the load impedance across the terminal AB that I need to determine. So the value of I naught, if I need to determine, I need to get what is the current which is flowing there. And if you remember our circuit in Norton's theorem, we have a Norton current I Norton in parallel with one impedance, that is the Z Norton, and then we have the load impedance ZL. So this is our ZL. Here I need to determine what is the current I naught. So I can apply the current division rule. I naught is equal to I Norton multiplied with the parallel of this. Okay, so you have like Z Norton divided by Z Norton plus ZL. Okay, so we have already determined Z Norton, we have determined I Norton, we have been given the value of ZL, so we can substitute that in this particular formula to determine what is the current which is flowing through the load impedance of 20 plus J15. So in this way we can obtain the load current I naught using the concept of Norton's theorem, where we will be requiring the KVL, KCL together with mesh and super mesh, as well as we will require some voltage division or current division rule. So these complete all the theorems with the frequency domain analysis, and the next class will start with AC power analysis.